Okay, let's keep going. We reviewed briefly the relevant information that we went over from the rigid rotor model. Let's see how that applies to discuss rotational spectroscopy. Okay, so first we should recognize, right, that rotational spectroscopy is going to take advantage of microwave incident radiation, right? That is the right region of the EM spectrum to get molecules to start rotating. We have our solution from the rigid rotor model, where recall J is our rotational quantum number, 0, 1, 2, 3, etc. And now we can make this equation just a little bit easier to write by noting that h bar squared divided by 2 times I will be unique for a given molecule based on its moment of inertia. So we call that the rotational constant. So we can have that in units of joules or in units of wave number. So recall when we use the little tilde, that means things are in wave number. And to get things in wave number, remember, we divide the energy in joules by hc. So for example, if I take h bar squared over 2 times hc times I get the following. I'm going to separate one h from another h bar by doing the following. So my h that I separated from this h bar is now 2 pi. And then now I still have all that stuff on the bottom, 2hc over I. So you can see that 1h will cancel with 1h. 2 times 2 is 4, and thus I get h bar over 4 pi c times I. Okay. So we can think about the rotational energy levels then in terms of joules, or we can think of them in terms of wave numbers. And of course, our spectrum is based on the difference of those energy levels. And we note that in rotational spectroscopy, we can only change one rotational level at a time. So let's start building up what our energy levels will look like. So if I have J is equal to 0, that's going to be my ground rotational state. It'll be somewhere down there. And now if I have J equals 1, it will give me the following. So with J equal to 1, and we'll stick here with just the joule solution. So 1 plus 1 is 2 times 1 is 2. So that level will be at a value of 2 times B. And if we take the difference between those, noting that when J is 0, this whole thing is 0. So thus the difference between the first level is 2B. So now what happens when we go up to the next level? Well, as we might guess, it spreads out a little bit. So now when J is equal to 2, we've got a 2 plus 1 is 3 times 2 is 6B. So the J equals 2 level will be at 6B. And thus the difference between J2 to J1 is given by 4B. So let's do one more of these so we can see a pattern. That J equals 3 value will spread out even further. And now when J is equal to 3, it's 3 plus 1 is 4 times 3 is 12. So now the J3 level will be at 12B. And now the difference between J3 and J2 will be 6B. So now this gets a little bit confusing. So I'm going to note this here as the following. So recall in our spectroscopy nomenclature, I write that J1 from 0, right? That nomenclature indicates the difference between these two levels. So that was 2B. J 2 from 1 was equal to 4B. J3 from 2 equals 6B. So hopefully you can see a pattern now there. That pattern is that the levels are actually spaced by every 2 times B. So I know that that's not immediately obvious looking at this, but what we have to consider is at a given temperature, there will already be molecules populated within these states, right? We'll have some type of population there. So all of these molecules or all of these states rather, are shifting up by 1. So in a microwave spectrum, we're going to see a whole bunch of peaks, and they are going to be separated by every 2 times B. So our selection rule, right? A molecule must contain a permanent electric dipole moment to have a pure rotational spectrum. If it doesn't have that, or in other words, if it doesn't have a moment of inertia, right, it doesn't have a rotational spectrum. J can only change by plus or minus 1. And so now if we look at a realistic spectrum, this is carbon monoxide at 40 Kelvin. And now we can see a whole bunch of sharp peaks here. And this frequency 10 to the 11 hertz, that puts us in the microwave region of the spectrum. And now, as you can see here, all of these peaks are spread evenly apart by every 2 times B, which is kind of cool to see. Okay? So let's keep going and take a look more specifically at these values. So here is the same spectra and the tabulated data from this spectra. So this is the same as this stuff down here. So now if we look at this here, the value in megahertz of the first level is given by 115,000, approximately 271 megahertz. So spacing from that previous line is 0. But now as we go up to the next level, you can see the spacing is given as 115,266. When we go up to the next level, it's not identical, even though I just said it was identical. And if you look through these, right, if you compare each of these as we go, what you will see is they are getting closer and closer together. So they're not quite 2 times B. So what's going on there? Well, as it turns out, we can't just rotate a molecule without affecting its bonds. So that's what we call centripetal distortion. So in other words, as our molecule is rotating around, it will have the effect of elongating the bonds as it rotates around faster and compressing the bonds as it rotates slower. And that will affect the energy levels. So I'll just present the solution to that directly. So remember, this is what we expect to give us every 2 times B, right? And the difference, okay? So if I say delta Fj. So, but now we can see, because as we get up to higher and higher levels, those values are getting closer and closer together. So then we know it's being subtracted. And there's this coefficient we can come up with called the distortion coefficient. And it's given as 4 times the rotational constant cubed times, and this is the vibrational energy of the molecule. So that is the vibrational spectrum. So vibrational spectral line. Okay. So we can't decouple the rotations from the vibrations and vice versa. So we're not going to ever see it truly be exactly 2 times B, but generally our first level, that first value we see, is a good indicator of the true 2 times B value, where the centripetal distortion hasn't taken as big of an effect at the smaller rotational levels. Okay, carrying on. So we also might notice that there's a really cool shape to this spectra and their lines. So I'll draw that with the following. I'm going to superimpose this curve on top of that. And as it turns out, that curve that I'm drawing on top of that is, you guessed it, a Boltzmann distribution. So this is pretty cool. So we'll get into why that's a Boltzmann distribution soon. In addition, we also want to note that our transition intensities are proportional to the expectation value of the dipole moment operator. This is true in all of our forms of spectroscopy. And this is the solution to the dipole moment operator directly, where mu is our permanent electric dipole moment, mu naught, permanent electric dipole moment, so the resting, equilibrium dipole moment. So the height of these peaks are affected by that. Additionally, the transition intensities are also proportional to the population of states. Or another way to think of it is the rotational lines are like a molecular thermometer. So using just a little bit of calculus, I won't show that here, but we can show that the max J value will be approximately equal to the following: T divided by 2 theta R square root minus 1/2, where theta R is known as the rotational temperature. So in the absence of molecular translations and vibrations, so at very, very cold temperatures, the only molecular mode responsible for that amount of heat are the rotations. And that's actually a very simple equation. It's given by the rotational constant divided by K Boltzmann. So the rotational constant has units of joules. K Boltzmann has units of joules per Kelvin. So that gives us units of Kelvin. So this is a very approximate equation, as noted by the squiggly lines, right? But that will also affect the intensity of our microwave spectrum. So I'm looking at that in a little bit more detail. Recall that we can describe the population of states with the partition function. So this is the rotational partition function. And if you recall, partition functions have the base value of being e to the negative energy divided by kBt. So now if we look at this here, we've got this 2j plus 1. That is our degeneracy. And then now here we can see this exponential, negative j times j plus 1 times b. That is our rotational energy, all divided by kBt. So if we sum all of those, all possible states of j, that gives us our partition function. And then now we can get the population of any state j by taking this exponential of only that particular state divided by the total molecular partition function. So you notice I've got this Mathematica thing going on here. So I've got a very cool calculation here where I'm setting up an approximate relationship where I've got my partition function as well as my dipole moment operator. And this is for the carbon monoxide molecule. And now I'm going to say that my population is proportional to mu times QR. So we can say that the intensity is proportional to the dipole moment multiplied by the partition function. And so we get something very cool here. So I had to start this at a minimum value. You can't start it at 0. And I chose 2.76 very carefully because that corresponds to 1 rotational temperature of 1 level. So now if I go up, if I arbitrarily make this temperature increase, we can now see that more of these J values appear in the spectra because at a higher temperature, I'm going to populate more J values. And so if I keep increasing the temperature, my rotational spectra will show me more and more lines, and I will get a wider and wider Boltzmann distribution from that. And then, of course, my max J value pushes out to higher and higher values as my temperature gets higher, which is pretty cool. So a microwave spectrum or a rotational spectrum can be used as a molecular thermometer in some cases. And then last, to wrap this up, we can also use rotational spectroscopy to investigate the types of molecules that are out there in space. So this is an actual microwave spectrum of the Orion Nebula, which is pretty cool. So you can see all of these really sharp lines. They are sharp because of how cold this temperature is, right? Recall the width of those peaks is not only a function of the lifetime of the state, but also a function of the sample temperature. So like when we see these extremely narrow peaks, we know that they're very cold. And additionally, we can work out what the temperature is based on the different populations of the lines that we're seeing. So for example, we see a line here for H2CO for formaldehyde. We also see another formaldehyde line right there. So likely this sample was a little bit warm to have two formaldehyde lines. We can also see a couple of carbon monoxide lines on here. And of course, depending on which isotopolog we're talking about, that will give us a different moment of inertia. So we can see all kinds of cool stuff in a microwave spectrum, particularly if we apply it to astronomy. Okay, folks, we're going to get into vibrational spectroscopy next. I will see you later.